Okay, my name is Jimborean. Nice to meet you. I'm a PhD student starting my third year. I'm in the University of Strasbourg, advised by my professor Philippe Claus and Vincent Loechner, and we represent the INRIA team Camus from France. And today I'm going to talk about our research work in LLVM, namely about handling multiversioning in LLVM, and specifically about code tracking and cloning. So to start with, I'm going to give a short motivation. Why do we need multiversioning? For instance, if you want to do sampling, but if you want to do instrumentation with a low overhead, we can achieve this by doing sampling. We instrument for a while and then we don't instrument, so we have very low overhead. Another solution would be for runtime version selection. That's in the field of adaptive computing. If you want to adapt a runtime to the execution context, you need to know which version you want to execute. So you need to have several versions prepared in advance. And finally, we can use this for any dynamic optimizations. Let's take, for instance, speculative parallelism, when again we can use the multiversioning approach. And to continue, why do we need multiversioning in different representations? For instance, if we want to connect all these ideas that I have given before in one, if we want to do dynamic optimizations, we first have to guide our optimization. So we need a profiling phase before. We need to do some instrumentation in order to know which decisions we have to take at runtime. For this, we have to prepare each version into the most suitable intermediate representation, depending on its task. Let's say that, for instance, we want to achieve low-level information using the instrumentation phase. With this, we cannot do, for instance, tracking memory accesses, because in the LLVM intermediate representation, the register allocation has not been done yet. So we need even a lower level representation. We have been working with x86-64. Maybe it's not really interesting for you, but you can apply the same for the ARM code. So with a low-level intermediate representation like the x86, we use this in instrumentation such that we can gather the low-level information. And then with this information, when we have enough, we use another version on which we perform transformations in order to optimize the code. For instance, if we want to do some significant code transformations, like for instance working on loops or any others, we can use the higher level intermediate representation of LLVM, which is more suitable because code manipulation is much easier in this. And not to forget, since we have multiple versions, we want to choose between them at runtime, so we need a runtime system that allows us to guide the execution. What are the steps when we perform multiversioning? First of all, since we want to be as transparent as possible to the user, we start from the source code. So we need to mark the code, and then we have to track the code until the LLVM representation such that we find back the regions marked for multiversioning. The next step is to do cloning. We want to perform cloning and then to customize each of these clones into the most suitable representation and for the task it has been designed. And finally, we need to update the control flow graph such that we can reach all the multiple versions that we have. What are the previous approaches for this? We start with the code tracking. This is mostly similar with the debuggers because they have to track code after optimizations, and this is actually very difficult. One approach that has been taken was by Brooks et al. That extend the debugging information and then create a map between the source code and the code obtained after optimizations. Another idea was given by Kumar et al., who take an extra challenge by debugging dynamically optimized code. In this case, it is really difficult to distinguish which one is the optimizer and which one is the optimized code. But there are approaches in this direction. Another interesting tool related mostly to our framework is the interactive compilation interface, the ICI, which is working with the Open64 compiler. The idea with the ICI is to provide access to the internal functionalities of a black box compiler. So it allows generic function cloning, generic instrumentation. It allows controls of individual passes for optimizations by patching the code. However, multiversioning in the ICI is available only at function level, which is not really suitable for our purposes, as we will see in a few slides. From the LLVM features that are mostly related to our work, or which were mostly interesting for us, was the fact that we can have support in the LLVM intermediate representation to preserve the high-level information from the source code. In addition to this, we can annotate the code using metadata information, which has no influence on the optimization passes, so it's very good because you can specifically write it just for the ones that you want, that you're interested in. And for multi-versioning, the cloning utilities that exist in LLVM are copies for instructions, for basic blocks, for functions. However, the problem is that there is no correlation between the original instructions or blocks and the ones that are cloned. Then it means that these functions or these cloning utilities can be used only in some very restricted situations. For instance, when you clone a basic block, you can only use it in the same function. You cannot use it outside of it. And let's see how did we overtake these problems. Tracking code in LLVM IR using attached metadata information. So first we start with tracking the code. From the source code, we identify the region that we want to instrument by inserting a pragma multi-versioning, which encloses between parentheses the full loop or the full loop nest that we want to instrument. We are focusing on loop nests because they are the most important target for optimizations. So we define this new pragma in Clang, and we have extended the Clang frontend such that we can recognize this pragma. And using it, we had afterwards in the LLVM intermediate representation several possibilities. Either we use barriers, so some dummy instructions that are enabling us to delimit the region of interest. The problem with barriers is, first of all, that they have to be some new instructions or some instructions that are not used anywhere else in the code. A second problem would be that the optimizations would eliminate them as dead code since they are not useful. But the most important problem is the fact that the order of the instructions might change, so you cannot find back your region after the optimizations. As you can see, either some additional instructions might be included, or even the instructions that were originally marked for multi-versioning will be excluded from the region. So we could not use this when we wanted to use higher optimization levels. The idea that we had in the end was to use metadata information. So for all instructions which belong to the region, we attach metadata information. And even if we apply optimization, the optimization passes of LLVM and their instructions are reordered, we still can find them back because we have the information carried on with the instructions. However, there are some problems because if we apply some very significant optimizations, the loop nest structure is changed. For instance, loop fusion, splitting, interchange, all kind of significant code transformations, and the metadata information is not preserved. So the approach that we took was to find back instructions that carry metadata information and to consider the whole loop nest that encloses that instruction, to consider it for multi-versioning. With this approach, with this strategy, we have more code included. In many situations, there is additional code included than the one that was originally marked for multi-versioning, but we don't lose any information like this. So it was not a problem for us to include more code in the region, but the interest was not to lose any code. Next, how do we do the cloning? So first, when we use the LLVM approach, this is what we obtain. We obtain some clones that are pointing back to the original version. So if we have BB1, BB2, and so on, and these are the relation between them, when we use the BB clone, we see that it points back to BB2 and so on. What we want is actually that it points to the corresponding clone. So to achieve this, we have to maintain a map between the original version and the cloned version. As you can see that BB1 is mapped to BB1 clone, BB4 to BB4 clone. And with this map, we can rebuild the control flow graph between the clones. And this is done both for instructions and for the basic blocks. Once we have done this, we can extract each loop into a new version. So we had the previous versions in the same place, but now we extract them into new versions. The reason to extract them into new functions, to extract each loop into new function, is that we want to compile each function independently, as I said, into the most suitable intermediate representation. So we have these new versions. We insert a call to these functions, and then we insert also a decision block that will allow us at runtime to switch between them. What were the problems that we had with multi-versioning? First of all, this is an error that you are all familiar with. So instruction does not dominate all uses. This this appears when we are using the cloning utilities of LLVM and then inserting the instruction immediately in the code. The problem was that if we go back to the previous slide, you can see that version 2 can be reached from the decision block before version 1. If in the version 2 we have the clones, but these clones are still using the original versions, we have this error. So the strategy, it's okay? The strategy was to first to clone, then to replace the uses in the clones, and only after that to reinsert the clones back into the LLVM code. Then the result is, as you see afterwards, the TMP use all original instructions, use only original instructions, and all clones use only cloned instructions before they are reinserted back in the code. Now let's see the interaction between high and low level intermediate representation. Why do we need this? Because we have a structure, the code structure that looks like this. So that we have the embedding LLVM code, which is in the LLVM intermediate representation, which goes into our new decision block. This is, in our case, represented in x86-64, which can choose either to do a call to a function that contains the original version or to a function that contains the instrumented version, which in our case will be in x86-64. So we always have to switch between them, between the LLVM IR and the x86 representation. And how do we do this? We need to communicate between the code versions, but also to ensure communication with our runtime system that ensures this switching between the versions. And the problem was that the control flow cannot enter or exit the lower level representation, because you know very well that inline assembly is expected to fall through to the following code. So the only solution that we found was to handle the control flow graph into the low level intermediate representation. And in the same time, we try to minimally influence the behavior of the original code. That is because if we want to perform instrumentation, for instance, we don't want to influence the code that we are instrumenting. And also, we don't want to influence the optimization passes, since we are always wanting to keep an eye on performance. How do we do this control flow graph? We need to insert, first of all, generic callbacks to the runtime system. These are patched by the runtime system. And this is because we want to be as generic as possible. So we want to have a framework that is able to do either instrumentation or optimization, but to prepare the code in a way as generic as possible. So we inserted these callbacks to the runtime system in the key points of the program in the following way. We put 0 in the RDI register and 0 in the RSI register, and then we make a call to this RSI, an indirect call, and we give some parameters to the runtime system, which at runtime will patch the correct addresses of the functions that are required to be called. Okay, so because of this, because we need to patch the callbacks, we have to have the code inserted at compile time on a fixed number of bytes, which is known and which doesn't change. So we have to protect our code from the optimization passes that follow. This is why we had also to insert the labels and to insert labels to know where we have to patch, to inform the runtime system where the patching has to be performed, and also to perform some jumps to these labels, because some of these jumps had to be patched as well by the runtime system. So this is the structure that we have for the jumps. We inserted the macro that simply gives the target, and this target is the label that we inserted somewhere in the code. So how does this work? Let's say that we have this control flow graph, a very simple one represented in LLVM. We are interested in the edges E1, E2, and E3. Because let's say that we have a new block, for instance, the decision block, which is inserted in the code, and we want this decision block to be patched because it contains a callback to the runtime system, because we want the runtime system to decide which version to execute. And since we want to patch these callbacks, we have edges which are represented in green here. The new edges are inserted in inline assembly, again to keep the code on a fixed size. So these edges in inline assembly create invalid LLVM code, because LLVM does not allow a basic block to terminate with a non-terminating LLVM instruction. So we need, in this case, to add also the LLVM terminating instructions. So we obtain like a control flow graph, which is a mirror of the LLVM control flow graph, But how does it work? We inserted the inline assembly jumps just before the terminating instruction, such that they are always taken. So the LLVM terminating instructions, the LLVM branches, are never executed because they are shadowed by the inline assembly code. With this, we achieve the fact that our code remains on a fixed size, so we can perform our patching, and we create valid LLVM code. Another problem was that if we don't insert these branches in all cases, I mean, there are some that are not shadowed. For instance, the new edge 0 is not shadowed by our assembly inline code, so we don't need to patch, but still we have to insert this one in LLVM, because otherwise the new block will be considered dead code and it will be eliminated by LLVM. So we need to maintain the control flow graph both in LLVM and in inline assembly, always taking care that our inline assembly code will shadow the LLVM branches and this will never be executed, such that only our code is executed in this case. Okay. What are the problems with this situation? From the beginning, in order to ease our hacking into the control flow graph, we needed to eliminate the Phinodes. So we promoted the register to memory easily using the optimization path rec to mem from LLVM. Once we obtain this, why do we need to do this? For instance, if we have these versions, we have the BB1 and the BB1 clone and so on. We extract them in new functions, as I explained before. But let's say that we have inside a V variable. We can see it in red on the left, and then we clone it into vclone. But somehow very late in the control flow graph, down there we see that V is actually used in a Phinode. And we now want to update this Phinode accordingly, such that it uses either V or vclone, depending on the path that we come from. But we cannot do this very easily. Why not? Because if we have multiple exit loops, like here we have the BB5 and the BB6 blocks, which are the exit blocks of the loop, and these are not in a dominator or post-dominator position with a BBN, where the Phinode is used, it's very hard to find. So the solution would be to find which is the exit block from which this BBN is reachable. In our case, we can see easily that it is coming from BB6. And in this case, we have to insert a new Phinode in BB6 and to converge together the values of V and vclone into this new Phinode, and then to replace later all uses of V with this Phinode. So it's an approach, and it works on some simple situations. But when we go to something like this, I'm not going into the details. I'm just showing a control flow graph of very simple example, which is optimized with LLVM. But as soon as we go, let me find this. As soon as we go into the SPEC examples, we have loops that look like this. So it's actually really difficult to hack into the control flow graph and maintain the Phinodes in the same time. Another problem when we promote the registers to memory was that if we extract each loop nest into a new function, we count on the fact that LLVM will transmit the correct parameters to these functions. That means all values that are defined outside of the loop and are used inside the loop, and all values that are modified inside the loop and reused outside of the loop are transmitted as parameters to these functions. And we use this in order to transmit the information between these versions, because these parameters allows us, for instance, to execute a few iterations in one of the versions, and then to transmit a number that we reached with the iterator of the loop to the next version, such that it continues from the correct point. However, if we eliminate the Phinodes, these iterators will be locals to the loops and then will not be transmitted as parameters of the functions. Therefore, when we extract in a new function and when we execute the loop, each loop will be reinitialized. Each version will reinitialize the loop from 0 when it is restarted. Of course, this can be easily solved by inserting some loads and stores between, but you have before the loop and after the loop, but you have to do this for all the variables that you're interested in. And the most important problem that we had comes here. I was mentioning that we need to maintain the control flow graph into the LLVM representation, but also into the inline assembly. Well, when we insert inline assembly code with labels and jumps, we have this problem that we want to jump to the label and before the Phinode is actually evaluated. The problem is that LLVM code does not allow anything to come before the Phinodes. So our label will have to be after the Phinode, will have to be inserted after the Phinode such that this is valid, which will provide us with some invalid or not correct code, because the Phinode will not be correctly evaluated when we go to that jump. So this is mainly the problem that we could not solve and which restricted us, and we had to promote the registers to memory to eliminate the Phinodes. The problem that comes from here is that we have more memory accesses. We restrict a lot of optimizations because now we have to go to memory and to come back to memory, so optimizations cannot do much with this. And we have a negative impact on performance on up to 25% overhead when we evaluate it on the SPEC benchmarks. So my question for you, because I know that you're all here familiar with the LLVM, is do you have a suggestion of how can we achieve this? So how can we do this patching on the control flow graph, but not to have to eliminate the Phinodes? Maybe we can take it after with some discussions. Another challenge that we had is how to handle the inline assembly, because we have to protect it really seriously against the optimizations. We have problems because the labels were duplicating, because of reordering of instructions, we were jumping somewhere where the label was misplaced. And we also had problems with deleting the inline code when it was considered as dead code by LLVM. The solution that we found was to create a new basic block every time we need to insert some new inline assembly in the LLVM, and to connect this block into the control flow graph using indirect branches. These indirect branches helped us in the fact that they prevented the optimizations, the LLVM passes, by not optimizing only those blocks that we are really interested in. However, the remaining of the code was still optimized. So this was the best solution for us. Another strategy would have been to insert metadata information on all this inline assembly code that do not have to be optimized, but this is really a headache because then you have to maintain all the LLVM passes and all the LLVM new releases with the new metadata information. So you have to make the new LLVM releases available of your metadata information attached. So this was not a good idea. We want to minimally influence the optimizers, so the optimization passes, but in the same time to maintain performance. I'm not sure whether this is the best strategy. Again, maybe you have better solutions. I'm happy to listen to them. Let's see the experiments that we have done. So I'm talking today in this presentation mostly about loop instrumentation, and we have done this by sampling. So we create the original version of the loop on the left and the instrumented version on the right. As you can see, we connect them with a decision block, and all the red squares that you can see on the slide are the callbacks that are done to the runtime system. So we have a callback to inform the runtime system that we entered the decision block, so a region that we are interested in for instrumentation. Then we have a callback before entering the instrumented version or the original version, and at the end of each iteration of an instrumented version. As you can see, the instrumented version of the loop, at the end of the iteration, goes back to the decision, so it loops, including the decision. But as soon as we reach the original version of the loop, we loop only inside. This allows us to limit the overhead, so we don't have to take the decision again. To mention also on here, I would like to say that we use this instrumented version of the loop to track the memory accesses. So for a few iterations of the loop, we stay into the instrumented version. We track all the memory locations that are accessed from that point. And based on this, we build some linear functions, if it is possible, which interpolate on the next memory locations that are going to be accessed by this loop. As soon as we have this linear function, or as soon as we reached a certain number of iterations, we go into the original version of the loop. What was the problem that we had? Multiple exit loops. Why? Because at the end of each iteration of a loop, we needed to insert a callback to the runtime system. So we did not know exactly where is the exit of that loop. But it was easy to solve because we already have extracted the loop into a new function, so we consider as the end of the loop the returning point of that function. Well, however, if we did not use this extraction, it would have been really difficult to determine where is the exit of the loop. Another challenge that we had to face was where to insert the instrumentation instructions. Do we need to convert that version, the instrumented version, into x86, or can we do it at the LLVM IR level? We decided for our purposes to do it in x86-64 because we had the register allocation already performed, so we know exactly which is the location that we obtain. Because in LLVM IR, we have to instrument all loads and stores, and this has a negative impact on performance because afterwards these loads cannot be eliminated. So they seem to be, LLVM considers them as in use and does not eliminate them, so we have more memory accesses. However, we perform the LLVM intermediate instrumentation on the LLVM intermediate representation for some other purposes. We will discuss this at the end. Another problem was that it requires type conversions in LLVM IR, because if you're familiar with the LLVM types, you can have either int on 8 bits, on 16 bits, on 65, or all kind of combinations. Then you have floats and doubles. You need to convert all of them to one unique type that you can send as a parameter to our runtime system. So this will require quite some work. What are the results that you obtained? First, I present here the SPEC CPU 2006. We instrumented the C and C++ codes from this spec. We have a runtime overhead reduced, I would say. In the case of the -0, so with the O0 optimization level, in most of the situations, it is very close to 0, the overhead, with the exception of the Xizheng and the Sphinx examples, where we had over 170 and 80% overhead. The reason was that we were instrumenting, in all these examples actually, we were instrumenting 3 top most time-consuming functions. So when we had these cases of Xizheng and Sphinx 3 examples, these functions contain some loops that were containing only 4 iterations, but were executing very, very, very often. So this means that we actually instrumented them fully. This is why we got a big overhead in that case. We did not take the advantage of the sampling. But it was easy to solve. You just disable instrumentation on these loops as soon as you find this kind of behavior. To go to the runtime overhead for the O3 optimization level, we can see that it varies. We have 0% in some situations, less than 4 in many, with a few examples over 10, and the most of it was 27 in the Sphinx 3 again. The reason is the Phinode elimination, because as soon as we create the original version that cannot be afterwards optimized because of this new loads and stores to memory, we can have very high overhead even when we execute the original version. And the last columns show the linear memory accesses and the percentage that we obtain out of those that we instrumented. We can see that we vary from 0% to almost 99 to almost 100% percentage of linear memory accesses that we detect. So this is very good for us, because as soon as we can predict the next location that is going to be accessed in memory, we can have a good idea for our optimizations. Another example, before going that, I have here a graph showing a comparison between the overhead with O0 and with O3. So we have in blue, in continuous line, the O3 example, which you can see is really low, and the spikes for the O0, which are for those 2 examples. So even with O3, even we had to prevent some optimizations, we still get rather good results, I would say. We have a good chance to optimize the code and to obtain good performance afterwards. To show the results on the pointer-intensive benchmark suite, this is not really relevant for the runtime overhead, because the execution time for these examples was very, very low, of the order of a few milliseconds, but is really relevant for the percentage of linear memory accesses, because it varies from 60 to 85, even in the case of memory accesses performed via pointers or indirect references and so on. To conclude, I would just like to make a summary of what we have talked about today. So it's first tracking the code from the source code into the LLVM intermediate representation using metadata information. Then we create multiple versions in distinct representation depending on the task of the version that we have. And finally, we control the control flow graph in the lower level intermediate representation, in our case in inline assembly. The perspectives that we have, we plan to use this instrumentation in order to perform speculative code parallelization on the fly, again using multi-versioning. This is already work in progress. And we can discuss about the problems that we have faced with LLVM also on this framework. Another idea would be to develop an easy-to-use API to extend our framework to embed more and more optimization and instrumentation possibilities. And let's see the challenges now that we had. The open questions are, can we promote the registers to memory without impacting performance, or can we do patching without having to eliminate the Phinodes? Another question is, do we have to maintain the LLVM branches and the jumps in inline assembly, or can we have, for instance, a new instruction in LLVM that will allow the user to maintain the control flow graph by itself, so to allow a non-terminating LLVM instruction for a basic block? And now give me a few seconds to talk about the type conversions. Why do we need type conversions in LLVM? Because for our speculative parallelization framework, we want to track all instructions, all values that are changed inside the loop, and we want to create this kind of linear functions interpolating on their values. So it's not only the memory addresses, but also the scalars and all other variables that are changing inside the loop. And with this, we have to cover really all types that exist in LLVM and to track their evolution. But we want to do this in a generic form as well. And we need to send this information to the runtime system with the value of the instruction that we are tracking. But the problem is that we need to convert all these types from LLVM to one unique type. So for instance, if you have let's say that we choose the bigger type, the double LLVM, and we want to transform an int1 to LLVM, then we need to a double, we need to extend it, then we decide it's a 0 extension or a sign extension. We extend it until an i64, then we can convert it to double. And as well, if we come from an integer on 65 bits, we need to trunc to integer on 64, and then again to decide whether it's a signed conversion or a not signed conversion to double, so on. So this was kind of a tedious work. If you have better suggestions of how we can achieve this, maybe we can discuss. And another problem that we have in LLVM, since we are starting for Clang, we don't have support for the OpenNP or for other parallelism, for pthreads. We have to do everything by hand in this case. So we have already discussed about it a little bit with some of the colleagues from here. We can take it further. Is there any path that can create this? Like if we want to insert calls to the GOMP library or to pthreads, is there a path that creates the structure required for the parameters that has to be sent, or how can we do this easily in LLVM? These are the open questions. Maybe we can take them after the presentation. Thank you very much. I'm happy to answer your questions as well.